This is the final lecture of the dimensional analysis section of the module, and the key parts of what we did was contained in the previous lecture, so I'm going to spend a few minutes just going over this. So we worked out what a dimension was and what a unit is, and effectively a unit gives us scale and a dimension tells us what the variable is, and we use 3, maybe 4 master dimensions to work out what the dimensions are of all of our other variables. And all of our equations must be dimensionally consistent. So if we've got a variable is equal to the sum of terms on the right hand side of an equation, all of these terms must have the same dimensions. So in spirit you must be able to say, if it's an equation about acceleration, then acceleration on the left hand side must equal acceleration term A, acceleration term B, acceleration term C on the right hand side. We also started to introduce non-dimensional groups. We came across one non-dimensional group called the Reynolds number, and we showed that by thinking about doing experiments in terms of non-dimensional groups rather than fundamental variables is a much better way to do this. You can reduce the dimensionality of your problem, and you should also plot results in a non-dimensional way. So that means that different experiments can be plotted onto the same graph, and you can exchange information between different experiments. And in this lecture, what we're going to do is we're going to do the same thing again, but I'm going to go through a formal way of defining how we develop these non-dimensional groups, and I'm going to introduce something called the Buckingham Pi theorem, and this is a method that lies behind how to develop the correct non-dimensional groups in your problem. Okay, so we did this example on the previous lecture, and it was an example where we said, well, we've got an object of size L and it's going with a certain velocity, and it's in a fluid with a certain density and a certain viscosity, and there's a drag force exerted on this object. And the question was, well, how do you represent this non-dimensionally? So if we apply, so we said that the drag depends on 4 variables. So we said that the drag depends on, or is a function of, the density, the length, and the velocity, and the viscosity. And we found that it depends on one non-dimensional group called the Reynolds number. That's what we did the previous week. So the Buckingham Pi theorem tells us directly that we need one group on the right hand side. Okay, so what we have to do is we take 3 variables that contain all of the dimensions present. So we've got 3 master dimensions. We've got mass and length and time, and so we need to choose 3 of the 4 variables that we chose. We need to choose 3 of the 4 variables that we had available on the right hand side. And in the previous example, I chose density and length and velocity. So the first step is to work out how to make the drag function non-dimensional. And we do this by coming up with a set of 3 simultaneous equations that we can solve for the 3 unknowns. This is why we need 3 variables to match the 3 dimensions that we have. Okay, so effectively we have this expression with drag and A densities and L lengths and B lengths and C velocities, and the question is, how do we work out the value of A and B and C to make sure that this thing is non-dimensional? So we've got the dimensions of drag. This is mass times acceleration. This is force. We've got density, so it's mass per unit volume. We've got length, and we've got velocity, which is length per unit time. And we've got A of these, B of these, and C of these. So this thing together must be non-dimensional. What are the values of A, B, and C? So we can do, what we can do is we can come up with three simultaneous equations for each of our available dimensions. So we know from this thing we've got one mass here, and we've got A masses here, and we know that there must be no masses in our non-dimensional relationship, so therefore 1 plus A must equal 0. And then we do the same thing for length. So we've got one length here, we've got minus 3A here, we've got B here, and we've got C here. So we end up with this equation here. And then time, we've got minus 2 times here, we've got no times here, no times here, we've got minus C times here. So we end up with this. And we can see from this that A is equal to minus 1. And we can see that C is equal to minus 2. And if we put A and C into this, we can work out that B is equal to minus 2. And we end up with our non-dimensional drag expression to be this. 1 density, 2 lengths, and 2 velocities. And then we said, well, that we've got one remaining variable that we haven't used in our functional relationship. And remember, we said that the drag must depend on these 4 variables. So we know that the viscosity must be in the non-dimensional group on the right-hand side. And there may be one or more of these repeating variables that we had on the right-hand side. So again, what we do is we say, well, we've got one viscosity, and how many densities do we need for our single viscosity, and how many lengths and how many velocities? And we go through the same procedure again. We end up working out these things here, and we can see that A is equal to minus 1, and C is equal to minus 1. If we put A and C into this, we can end up working out that B is equal to minus 1, and we end up with our relationship here. And this is Reynolds number. Actually, this is 1 over the Reynolds number. But that doesn't matter because we don't know the functional relationship at the moment. Okay, so we've got two groups of variables here, and it's quite important to distinguish between these things. So what we call repeating variables and remaining variables. So the repeating variables are the things that appear in both of our non-dimensional groups. So rho, L and U, they all appeared in our drag expression, and they also appeared in our Reynolds number expression. Okay, and they mustn't be able to form a non-dimensional group on their own. So what I mean by that is, can I form a non-dimensional group out of density and length and viscosity without adding another variable? And the answer is no, I definitely can't, because density has a mass dimension, and length and velocity have no mass dimensions. So it doesn't matter how many lengths and how many velocities I use, I can never make density non-dimensional. So that's all good for that. And they all contain all the dimensions. So mass, we've got mass and length and time, so we're okay there. So these two things are the key sort of metrics for defining a successful and valid repeating group. Okay, and then the remaining variables are just simply everything that you didn't include in the remaining in the repeating variables. So drag was one, and that formed a non-dimensional group, and viscosity was the other, and that formed another non-dimensional group. Okay, so the problem really has 3 steps. Work out the number of groups that you need. So you do this directly from the Buckingham Pi theorem. and work out what your repeating variable group's going to be, and then with all of your remaining variables work out your non-dimensional groups using your repeating variables. Okay, so let's do another example. So this is slightly different, different number of variables present here. So got a hydraulic jump. So this is when a high-speed flow instantaneously slows down and goes through a change in height. So here's a nice example here. You can try this at home. And we've got two length scales. So we've got the thickness of the liquid layer before the hydraulic jump and the thickness of the fluid after the hydraulic jump. And other relevant variables are the velocity of the fluid, the acceleration due to gravity, and the fluid properties. So in this particular case it's the density and the dynamic viscosity. Okay, so we make a statement that says y2, so this is the thickness of my fluid after the hydraulic jump, depends on these particular variables. So y2 is a function of y1 and u and density and viscosity and gravity. Okay, so the question is, what are the non-dimensional groups here? How do we write this? Okay, so on the right hand side we have this one. We've got 5 variables, and we've got 3 dimensions. So if you use the Buckingham Pi theorem, which is the number of variables minus the number of dimensions, we get 2. So of these 5 variables on the right hand side, we're going to generate 2 non-dimensional groups, and we're also going to have a non-dimensional group on the right hand side, which is going to be a non-dimensional group with y2. Okay, so now we have to come up with our repeating group. So we need to make sure that we have dimensions. We need to have all of the dimensions in our repeating group, and we need to make sure that we can't form a non-dimensional group with our variables on its own. So we've got three dimensions, so that means we need 3 variables in our non-dimensional group, and we've got to choose 3 from these, and we mustn't make a non-dimensional group on their own. So what we can do is we choose our least common dimension, and that's mass, and we see that we've got 2 variables with mass in it, so we choose one of these to be in the non-dimensional group, in the repeating group, and not the other, and that guarantees that we can't form a non-dimensional group with our repeating variables. So we'll choose density for sure, and we'll have a velocity, and we'll have a length. Okay, so y1, u, and rho are our repeating group. So we've got to find a non-dimensional group with y2 and our 3 repeating variables, and g, because this is one of our remaining variables, and the other 3, and the viscosity and our 3 remaining variables. Okay, so how do we go about that? So we just do this 3 times. So let's do the first one. Here's my geometry. This is my functional group, so I'm going to have one. The question is, well, for each y2, how many y1s and u's and rho's do I need? So I need to form a non-dimensional group with these 4 variables. So effectively I've got to choose what A and B and C are. So if I go through here and I compare my mass dimensions, I've got no mass dimensions for this, no mass dimensions for this, no mass dimensions for this, and I've got 1 here. Okay, so C, 1C, it's got to be equal to 0, so that tells me that there's no densities in this. And then my lengths, I've got 1 here, A here, B here, minus 3C here. So here's my simultaneous equation. And time, I've got no times here, no times here. I've got minus B times here, and no times here. So that gives me C and B at 0. And if I work out this, it shows me that A is equal to minus 1. And my non-dimensional group on my left-hand side is simply the ratio of these lengths, which seems sensible. And I'm not going to go through all the steps, but you can do this on your own. So the next one would be taking gravity and so your next group would be gravity, and how many y1s and u's and rho's do we need to make that non-dimensional. And the last one would be viscosity, and hopefully you recognize this one as the Reynolds number. So we've come across one more extra non-dimensional group. This is called the Froude number, and so this is important when you have free surfaces present, effectively. So this is the ratio of momentum divided by gravity. Sometimes you see this as the square root of this sign. Okay, so from the previous lecture we introduced the idea, and this lecture we've kind of introduced the way to come up with these non-dimensional groups, and we've come up with a system. And the key thing is you have remaining variables and repeating variables, and the key step is choosing your repeating group correctly. And once you've got your repeating variables, you can then go through and work out your dimensionless groups directly. And we've introduced another non-dimensional number called the Froude number. Okay, so the way that I've proposed this is not the only way to do this. There are several different ways to do this, and there is another method called a matrix method, and this is explained in the Crow edition that I've highlighted in my recommended reading. Okay, thanks very much.